Welcome to the Deep Dive. Today, we're plunging into, well, one of physics' most mind-bending paradoxes, the Born rule. Imagine a fundamental law, really fundamental, underpinning quantum mechanics. It's confirmed with, incredible precision. But, and here's the kicker, it's still technically considered unproven at its theoretical core. That's the enigma we're unpacking. We'll look at Max Born, the mind behind it, the huge shift it caused, and, why it's still debated. So let's set the scene. We're in 1920s Göttingen, a real hotbed of science back then. Max Born, a mathematician initially and a fantastic mentor, was right in the thick of this quantum revolution. He did something crucial. He took Werner Heisenberg's new physics, which looked really strange, all these arrays, and he recognized it. He saw it was actually sophisticated math, matrix algebra, which was pretty groundbreaking because matrices don't always commute, right? Order matters. And that captured the weird jumps in quantum stuff, unlike smooth classical physics.
Yeah, what's fascinating is just as people were wrapping their heads around matrices, Schrödinger pops up with wave mechanics, a totally different picture. He's describing quantum systems with these continuous wave functions, this ideas, and this created an immediate problem, a real dilemma. If Schrödinger is a smooth wave, how on earth does it explain the particle-like hits we see? The click in the detector, the single dot. Schrödinger himself really struggled with what it physically meant. He thought maybe charge density, but no, that didn't work out. His math was beautiful, but the meaning, kind of a dead end initially.
Right, so the guy who invented it was stumped by what his own wave function actually represented physically. That sounds like a crisis. How do they get past that?
Well, this is where Born comes in, 1926, and he makes this incredibly audacious leap. He proposed that Schrödinger, the wave function, doesn't describe the particle itself. Instead, it describes the probability of finding the particle somewhere. And crucially, it's not K-day directly, but the square of its amplitude, T-day 2. That gives you the probability.
Okay, so the higher the wave's amplitude squared at a point, the more likely the particle is there. That wasn't just tweaking the math, was it? It was a huge philosophical break. Suddenly, classical determinism, knowing everything at the start, lets you predict the future perfectly. That was just gone. Which really bothered Einstein, right? In his famous God does not play dice line. And Born basically replied, well, actually, it seems he does. It puts randomness right at the core of things.
Exactly. And this leads us to a really central question. If this Born rule is so fundamental, so accepted, why do we still say it's unproven? Well, in the standard Copenhagen interpretation, it's not derived. It's a postulate, an axiom. We accept it because, honestly, it just works perfectly in every experiment. Now, there's a theorem by Andrew Gleason, quite powerful, which shows it's essentially the only rule that fits the mathematical structure of quantum mechanics, given some reasonable assumptions about how probabilities should behave. But that's still not deriving it from some deeper physical principle. Other theories, like many worlds or pilot wave, they try to derive it, but they need their own assumptions, which are themselves debated.
So it's basically a foundational rule we use because it works, but without a clear why from first principles. That sounds like, a bit of a leap of faith for physics, doesn't it? How can we be so sure it's right if it's not derived from something more basic?
But that's the clever part. How do we get so confident? By testing what it forbids. See, the rule is quadratic. It involves squaring the amplitude, say 1300. This mathematical structure strictly means that interference, the wave patterns, can only happen between pairs of pathways, two paths interfering. It absolutely forbids third-order interference or anything higher, three or more distinct paths interacting simultaneously to create an interference effect. Born says no. If that happened, it would break the rule, suggests probability isn't purely quadratic.
That's smart. Test it by looking for something it says can't happen. So how do they actually look for this forbidden interference?
Right, so connecting this to experiments, scientists use these really ingenious setups. Things like multi-slit interferometers, but designed for 3 slits or paths, or sometimes single quantum systems, like spins and diamonds, manipulated to have 3 possible routes. And they measure something called the Sorkin parameter. It's designed specifically to be 0 if the Born rule holds. Any non-zero value would mean, there's some forbidden higher-order interference going on, and the results. Across decades, different systems, consistently 0, or incredibly close to 0. The precision is amazing, sometimes less than 1 part in 10,000, even $105. So empirically, its predictions are just absolute. By testing the limits, we're really probing the fundamental structure of quantum probability itself.
Okay, so where does all this leave us?
Yeah.
The Born rule is this massive pillar of physics. Empirically solid, never failed a test, yet theoretically, it's still this fundamental postulate, this mystery. It works flawlessly, but we're still debating where it ultimately comes from.
Yeah, that feels...
Well, it challenges how we think science should work, right? Shouldn't our best laws be derived?
It definitely forces us to confront big questions. Is randomness just baked into reality at the deepest level? Or is there some underlying deterministic layer we haven't found yet that just looks statistical to us? The question isn't is Bourne's rule works, it clearly does. The question is why.
Yeah, it's a powerful reminder, isn't it? Even with our most precise theories, the universe can still keep secrets about its fundamental operating instructions. We hope this deep dive into Max Born and his rule gives you plenty to think about reality and maybe the limits of what we can know.